This is a show that I and two other the curators here in the Space Science Department, Steve Lee and Kachun Yu, do a program every month on the latest happenings in space sciences. Generally, there's two of us giving the presentation, but both Steve and Kachun are out of pocket today, so I get to fly solo. And it's always a very fun program because, we never seem to run out of things to talk about here. And I've got plenty, I think, to talk about here today. So I am actually going to get started early. So at the end of the program, if you got any questions on any of the stories that I talk about, we open up things for questions at that time. So without further ado here, I'm going to get started here. And one of my main stories is going to focus on the Dawn mission. Earlier this month became the first spacecraft to orbit a dwarf planet. As you might recall, the dwarf planets, Pluto is now a dwarf planet. So, and it got demoted to dwarf planet, whereas Ceres actually got upgraded to a dwarf planet. And so the New Horizons mission to Pluto will get there later, I think in July here. So Dawn beat it to that. Now, the interesting thing about the Dawn mission is it's actually gone to two other solar system bodies. It started off and launched in September of 2007, got a gravity boost from Mars in February of 2009, and then it orbited Vesta, another one of the, and I'll talk more about Vesta later here, where it was there from July 2011 to September 2012, and then it left from Vesta and has now just arrived at Ceres. So this is the first spacecraft to ever orbit two bodies. It turns out, how can you actually do that and not break the budget? Well, it turns out we don't have the capabilities with a single spacecraft, or not a single spacecraft, but a spacecraft with normal propulsion to do that. So what this spacecraft had was what's called ion propulsion. So I'm going to talk a little bit about what that ion propulsion is. Who are Star Wars fans out here? So what is that spacecraft there in the middle? The TIE Fighter. TIE is an acronym for Twin Ion Engine, okay? So George Lucas knew we were going to have these ion propulsion systems long ago here in a galaxy far, far away, yes. And the way an ion beam engine works, and where any propulsion system works, to move yourself in space, you've got to push on something. Well, you can't push on space, you've got to push on your propellant. So you push that in one direction, and the spacecraft goes the other direction. To improve the efficiency of your propulsion, you want to push on that propellant as fast as possible. So you want to eject it out the nozzle at the highest speed as possible, and we can do that with ions. And basically you have a chamber that you create an ion, which means you take an electron off, in this case xenon atoms, and when it's been ionized, you can accelerate that in an electric field and shoot it out the back, and then that propels you in the opposite direction. Now, the problem with our ion beam engines at the moment is they have good efficiency. In other words, they get a lot of bang for the buck in terms of how much they put out, but they do not provide that much thrust. So it's a very slow process, and that's why it took so many years actually to get to the two asteroid bodies here. Here's actually a picture of that. So they do really have a kind of this is in the laboratory, they have a kind of a blue flame that comes out the back. So whenever you, and then to get the energy from that, the spacecraft, to accelerate these, xenon atoms out there, they have to have huge solar panels that are creating electricity to ultimately accelerate these particles. So the next time you see, Star Wars, I don't think the Dawn spacecraft is quite as fast. So anyway, I want to step back a little bit here and talk a little bit about the dwarf planet that the Dawn mission is going to. This was the solar system that we knew of in 1800. Okay, You can see it goes out to Uranus, and Uranus was discovered, I think, in like 1764, and we were happy with that. But then came in 1801, basically, on January 1, Giuseppe Piazzi discovered this body out between Mars and Jupiter called Ceres. And Ceres is actually the name of the goddess of agriculture and grain. And so here's a statue of her, and she's holding her, grains and fruits and things like that. And the name cereal comes from that. I actually did not know that, so I just learned that actually this week. And so here we were at 1800, and after in 1801, here we discovered Ceres, and this is where it laid in the solar system there. So that seemed to fit nicely with, this kind of gap in between here, and there was like no problems, with that object being there, and Ceres for a long time was a planet. Okay, and then the next that relates to the dawn image is Heinrich Olbers, who, if you ever heard of the Olbers paradox and things, that's why the sky is not dark, proves that the universe is not infinite. But anyway, he was an astronomer that I think about 4 years later, discovered a fourth object, which turned out to be Vesta. There were two other objects that were found out there that were a little bit smaller than that, but Vesta turned out to be the second biggest object in this area. And Vesta is the goddess of hearth, home, and family. And I'll talk about their encounter with Vesta a little bit more. And here's where Vesta fit in the grand scheme of things. And it was a little bit interior of the Ceres, but still fit nicely with what our knowledge was of the solar system at that particular time. So in the 20th century, however, we started to, oh gosh, my dots are not showing very well here. We started to find more and more objects. Can you guys see objects around here? Yeah, little dots over here. Okay, good. We started to find more and more objects there. Okay, yeah, so there should be a lot of dots around there. Can you see them over here and over here? Yeah, you can see some there. So we started to find a lot of objects that existed between Mars and Jupiter. And to a point that it got so much that, and looking at it in the grand context of the solar system out to Uranus here, it got to be so much that Ceres and Vesta and several others were then demoted from being planets. So remember that theme, okay? So why are all these objects? I mean, if you look at the solar system, it looks like there's something very unique here about this region here. Everything else seems to be fairly empty. It's empty interior to Mars here, and it's empty outside of Jupiter here, but there's a lot of these objects in here. So what is actually going on there? Why do we have so many objects there? Well, you have to kind of look at the dawn of our solar system, dawn not being pun intended here, because this is why the dawn is called the dawn mission. But you have to go back 4.6 billion years when things were coalescing together to form our solar system. And then at that time, things were accreting together where we had dust to form rocks and accrete rocks to form planets. But as they were starting to form, the massive effects of Jupiter started to basically interrupt that process of planet formation that was occurring between Mars and Jupiter. And so Ceres and Vesta turned out to be the largest objects in that, what we now call the asteroid belt, and astronomers consider these to be protoplanets. They didn't quite make it to planetdom because they didn't get big enough. And another definition of our planets now is they got to clear the space around them, and these objects do not do that. But they are large objects, and as I'll show, they really are distinct from the rest of the asteroids that are out there. So basically, when we are exploring Vesta and Dawn, we are getting insights into, Vesta and Ceres, we're getting insights into the dawn of the solar system, and that's what the Dawn mission is all about. So here are those protoplanets in reference to the largest asteroids out in the asteroid belt, and you can see they are quite different size objects. So they are, you know, big, and they have, what I'll show, they have structure interior. These are pretty much just rocks there. And if you look at them the scale of other solar system bodies, you'll see that they're pretty large. You can see Ceres is pretty close to the size of Pluto. And you can see that by reference, the California here, people control the Dawn mission route in California, so JPL. So they're going to reference into California. You can see that it's substantial to the size of that state. Now, this is a flat map here, so a better way to actually look at how big Ceres is that if this is a map of Ceres out to, well, only to about 60 degrees here, but here's the amount of area that's covering Ceres here, and you can compare that to the area of the United States. It's not as big as the United States, but it's very substantial. I think it's about 4 Texases put together is how much area that you have on Ceres. So there's going to be a lot to explore over the next months to I think the official mission end date is like June of next year. And so one of the things about being so big is that Ceres was large enough to develop a core where it has a nickel iron core here, or what we call rocky core here. It has a water ice kind of mantle out here, which has the potential of having potentially liquid water still there, and we'll find that out when we start studying this particular dwarf planet. And then a thin icy crust on there, on the outside. So these are really distinct objects from the rest of the rock, basically rocks that are in the asteroid belt. And here is just a video showing what really kind of transpired here over the last month here. The spacecraft is actually still getting into orbit, and I'll show you a little bit more about that orbit. There's ion beam orbit engines there, and it's going to be very interesting when it gets to Ceres. You'll see how it actually gets around Ceres itself. Just showing some photos, and there over the last month there hasn't actually been any new photos that have been made of Ceres, but I'll show you the most recent ones there. And then in particular, they're showing that's one of the ones that they had. We had the bright spot here, and so these are actual photos that they were taking along the line. And when I talk about Vesta a little bit, you're going to get to see, really how good this thing is going to do to map. And I'll show this one later, but here is a composite of different images. You'll see those bright spots that actually rotate into the field of view. We still don't know what those are. And we'll get closer, and here is it coming into orbit. So they don't have a lot of thrust there, so they're making this big swing here. They're giving as much thrust as possible with those ion engines, and then it circles back over the poles, so it's going to get a polar orbit. And the advantage of those polar orbits is you can map the entire planet that way. And then notice the thrusters went off, and in essence, you're now trapped by the gravitational forces of Ceres itself. Okay. So when this is still going on here, but it's going to actually attain 4 different orbits here. So it's currently, and I think it's April, it's going to be in this RC3 orbit, about 8,400 miles above the surface. That's the diameter of the Earth, or the radius of the Earth, basically, in terms of distance. And then it's going to go down to survey mode, which is 2,700 miles here, and then down into this, what they call the high altitude mapping observing mode. I guess I forgot what the O is. Orbit there, yeah, which is kind of a misnomer since it's not the highest altitude. This is over here, but then it'll get down to the low altitude mapping orbit there, which is 230 miles, which is a little bit closer than the International Space Station flies over the Earth. So we're going to have a very bird's eye view of this. And I was thinking that we had this projector problem last time, didn't we? So Kim, do you remember what it was to maybe fix on it there? I, you know, these are looking kind of faint. I'm a little bit worried when I get more to the end of the talk and I'm showing nice space pictures with stars that that's not going to look good. So I don't know if we want to mess with it at any time here. And so here is as it goes down from the high altitude to the low altitude mapping orbits, and you can see it takes a lot of orbits to get down there, and that's because of this ion engine there that only provides a little bit of thrust to slowly wind on down to get to that orbit. And once it gets to that orbit, it's going to be there forever, essentially. When the spacecraft dies, it'll just continue to orbit, and I guess it'll be a artificial satellite for Ceres all that time. I wanted to just say some stuff about the Dawn mission to Vesta here, just because this is kind of the results that you can expect when we get to Ceres as well. This was the Hubble image of Vesta before Vesta got there, and it turned out that we have a lot of meteorites here on Earth that come from Vesta, and there are only 3 objects in the solar system that we know where the asteroids come from, or the meteorites come from: the Moon, because we've had men there to retrieve samples; Mars, from the Viking mission there, they measured the atmosphere of Mars, and we can identify meteorites that have been from Mars based on trapped gases in the meteorite itself that match up with the composition of what we know about the Martian atmosphere. And Vesta, because Vesta has unique spectral signatures, and when we look at Vesta, we can tell that those spectral signatures are the same as these meteorites we had. And we had a huge class of them here on Earth. And it turns out that about 6% of all meteorites found on Earth have come from Vesta. And why do you say they come from Vesta? Well, even in the Hubble images here, you could see that this object looks pretty round up here, but there was some serious deformation over here on the south end of this protoplanet. And so here is the image that was taken by, or composition image that was taken on the same scale from the Dawn spacecraft. I'll show a little bigger view here. And here's that interesting southern area here. Look at these bands that come across here as well. So Vesta, we now know, got hit by a large object from this side over here about 1 billion years ago, and this created this big crater that is on this side over here, and I've got another image of showing what's over there and everything. And these little bands that you see across here were due to when it got struck, it almost broke it apart, that the whole protoplanet reverberated a bit and then settled here. And you can also see that things on this side are much more cratered than this, because that impact wiped away all the cratering history, and these are all relatively fresh craters over the last billion years or so, whereas this here is back to, the early days of 4.5 billion years that you're seeing evidence there. So very interesting impact. And here's an image that they've now created, a movie basically, where they draped it over the topography so you really can get a sense of how this object looks. Look at that band that's across there around its equator. And then it'll fade here to the South Pole, where you'll see this huge mountain that is on that one side. So we can expect similar things from when we get to Ceres. I'm going to go to the next slide here. And yeah, this is starting to look, does that look dark to you guys? That looks okay? Okay. Here's a formation is really cool to see. Up here are some of those canyons, these really deep canyons from that point where the protoplanet buckled here, and this is what they call the trio, or the snowman craters here. over here. So that's one of the cool images from there. And here's like a topo map showing that southern mountain from the impact and everything, where blue is minus 14 miles from kind of the average distance here, and the top of it is close to 12 miles there. This distance is twice the height of Mount Everest. So this is the second largest mountain essentially in the solar system, rivaled only by Olympus Mons that is on Mars. So really cool structures. Other things that they can see from the cameras and stuff. Here's a black and white image. You can see some stuff that's going on, but they have essentially color filters that they can also look at. And one of the things that they do is they look at the ratios of how much red light do you have to blue light, how much or blue light to red light, and they also have ways of picking up iron. So they create these nice color composites that are essentially false color that really accentuate the different minerals that you're seeing in the surface. And so they've actually created a map too here, seeing the different compositions of the surface in this movie here. So it's the same as before. In the interest of time, I'm going to click through that one. I hate to say. So they've, named all the craters and such after the Vestal Virgins and their famous Roman women there. So they'll do a similar thing for Ceres. So there'll be names like cornflakes and Cocoa Puffs and things like that, right? Here's that image again. You saw those bright spots that came around there. And so those bright spots right now just are places where the reflectivity is a lot higher. They don't know how much more reflective because in these images, they haven't resolved what is reflecting light so well at that point. It's not saturating the detectors or anything like that. It's just that there's probably, been hit there. It's probably newer material that has actually been exposed. But anyway, that's the things that we get to find out. So here's, basically the map that we have now. And like I said, they haven't turned over any more images and things, but they haven't really started their mapping campaign because they haven't attained their various orbits. The next thing I wanted to actually talk to you about is earlier this month we had a kind of a simulcast between Adler Planetarium and here, where Mike Brown, who is the guy who killed Pluto, talked about other discoveries that they've had out beyond Pluto, and he had some interesting results which I wanted to actually report here. I did read this book here in preparation of that, and it's a very good book, and it had some interesting intrigue in there with astronomers finding out where other astronomers were pointing their telescopes so they could, in a sense, steal their discoveries. So I didn't even know that kind of stuff went on. So that was very interesting. So, so he started this whole debate of what ultimately demoted Pluto to dwarf planet because his discovery of Eris, which is now known to be larger just a little bit than Pluto. And here is its orbit relative to Pluto. And you'll see other objects that we have actually found out in the same region, which we call Kuiper Belt objects. And Eris and Pluto are kind of the biggest objects in this area. So does it sound kind of familiar with what's going on with the asteroid belt? So here are these objects, which they call trans-Neptunian objects, TNOs. And here's where Eris fits on there. There's Pluto. You can see it's just a little bit bigger there. We now know Pluto has quite a few moons here. Eris has one too there. And he was the discoverer of this. And Mike Brown's wife's name was Diane. So this was actually in why he came up with that name there. So you get to name your discoveries. And this has been updated with some other objects here too that are in this larger class of these particular objects. Now, the interesting thing that he talked about there in the talk were, here's a map of all these objects that we know, well, not all the objects we know, but ones that are out from 0 to, this is in astronomical units, where astronomical units is the distance between the Earth and the Sun. And so Pluto, which is right here, is about 40 AUs away from the Sun. It's actually the semi-major axis, which means if you take the closest point and add it to the longest point that it's from the sun and divide that by 2. That's the semi-major axis. Pluto actually gets closer than this, but also gets further as well. But its kind of average distance is 40 here. And you can see all these other objects that we found out there. So there's a mass of different objects, just like there was a mass of different objects around the asteroid, and was one of the central reasons why these objects were not called planets, and they were obviously not influencing the objects that were around there, because there are a bunch of them. Well, they started looking at several objects that are called these extreme trans-Neptunian objects that are out at astronomical units of like 150 AUs out there. An example one of those is one of those objects that was discovered was called Sedna. Here it is relative to the rest of the solar system here. Jupiter here, we're going to go back out a little bit here. Here we see out to Pluto. Here is Sedna. And then as we go to the next panel here, Sedna was discovered very close compared to its very, very elliptical orbit. It takes it way out in our solar system here. But we even have stuff further out in there called the Oort cloud that you see here. So this is one of those objects, and they've discovered other ones, and in this graphic they show this one, 2012 VP113. It too is out in these orbits as well. They studied about, in January they actually announced this, they were looking at about 13 of these objects, which are these extreme trans-Neptunian objects there, and they find that they are a lot different, and their orbital parameters are a lot different than what they should be compared to the models of objects that would actually have formed out there. First of all, they should have much more circular orbits. They should also have orbits that are not inclined that much from the rest of the what we call the plane of the ecliptic, where other objects orbit the sun. And so those were off, and they seem to be aligned in a way that if you were looking at all these elliptical orbits, the closest points are all kind of to one side. And the best explanation of that is that we have a giant planet on the order of the mass of the Earth that's influencing these orbits. And so Mike talked about that a little bit in his talk. And right now, based on the number of objects that they had right now in the study, there's about a 5% chance that this is random, that you just happen to line, things up on one side, just like if you, flipped a coin, 10 times and it came up, whatever, I don't know, 8 times heads or whatever the 5% chance is that would happen. But the most likely thing that it's pointing to is this giant planet that is potentially out there, and the possibility of actually having 2 of those that are out there. And these would be actually classified, if we find them, as a real planet. So anyway, that I find very interesting. A lot of the solar system models just can't seem to produce planets out there at that distance, but we have some other evidence. Kachun talked about this image, which is taken in the sub-millimeter part of the spectrum of a particular star system that's imaging the disk forming around another star. This star is just now starting to form planets, and these gaps that you see out here are actually due to planets that are sweeping out material in those gaps. These happen to be out there at hundreds of AUs. So we at least have one system we're seeing planets form at that kind of distance. So it goes against some of the theories and stuff, but there's contradicting evidence suggesting that these things might actually be there. So the thought of having another planet is going to be a cool thing for discovery, and young people out there want to be astronomer, you can be the next person to discover a real planet again here in their solar system. I figured I should say something about the mission to the Rosetta mission to this comet. I won't try to pronounce it. And I don't know if you can see here, but this is taken by the NavCam. Was taken earlier this month, just actually last week, and there's jets of material that are coming out of this here. So this comet's getting closer to the sun. They're observing it. A lot of it's coming around this neck. It's these 2 objects that look like, it banged together and stuck a little bit, but there's like this weak point here between there where it's evaporating more. They announced that they discovered for the first time molecular nitrogen in a comet around here this month. But the interesting thing I thought was this set of images here. So here's an image and it's maps from this square, because it's looking kind of at an angle here, to this square here, progressively getting bigger, to this square right here, and then that square gets mapped over to here, and you can see it looks quite a bit different, and that's because there's a lot of shadow here. The sun was at an angle here. The sun is almost directly straight on here. And what is that? Seeing more here. What is that? It's its shadow. Okay, so first time they ever got their shadow in the place. So they see the shadow of the spacecraft. It's very blurred out because you'll notice, like if you look at your shadow of your hand against the ground, you can get a nice sharp outline. But the further you bring it out, the more and more blurred it actually gets, and that's because the sun has some angular size. It's not a point source of light, and it casts a blurrier shadow compared to something that would be at a point there. So anyway, I thought that was a very cool observation.